So now in this class, we will take up a problem on cantilever beam. How to draw the bending moment diagram and shear force diagram for a cantilever beam subjected to external loads. So here I have considered a cantilever beam AD carrying a concentrated load at B 8 kN, an external moment, anti-clockwise moment 20 kN at the same point B. Then there is a triangular load of 10 kN/meter to 0 varying from C to D, and the spans are given as 2 meter, 1 meter and 2 meter. Now you know that in the case of cantilever beams, one end is fixed and the other end is free. Here end A is fixed end D is free end. So reactions will develop only at the fixed end, there is no reaction at the free end. So there will be two reactions here. Since it is subjected to vertical loads, you have vertical reaction VA and a resisting moment MA. So this MA will be in this direction because the moments due to these given forces will be in the clockwise direction about the point A. Therefore, to resist that moment, there should develop an anti-clockwise reactive moment at A, which is nothing but MA. Now the first step is to find the reactions as usual. So reactions are very easy to find in this case. Anyway, we are using equilibrium equations. So first equilibrium equation is total upward forces should be equal to total downward forces. That is nothing but your sigma Fy is equal to 0 equation. So if you use that equation, Va is the only upward reaction here. That should be equal to total downward forces. That is 8 kN plus this. So this UDL triangular load is converted to equivalent concentrated load. So equivalent concentrated load is nothing but area of the triangle. So which is nothing but half into 2 into 10. So that means your total downward force is 8 plus half into 2 into 10, which is nothing but 18 kN. That is equal to your reaction. Please note that when you are calculating the vertical reaction, the external moment is not considered. So this 20 kN is not considered. Now the second equation is moment equation, which is nothing but sigma Ma is equal to 0. Or in other words, so to find this reaction Ma, I have already told that the reactive moment should be equal to the algebraic sum of the moments caused due to the externally applied loads taken about that point. Now since I have the reactive moment develops at Ma, this Ma value will be equal to all the sum of all these clockwise moments and also the external moment given in the problem. So Ma is equal to, here moment due to 8 kN is 8 into 2. So that I have written here. Then moment due to this triangular load is half into 2 into 10, and we assume that this triangular load will be acting at the CG of the triangle, which is at a distance of 1/3 of 2 meters from C. So that is 0.67. So this distance is 0.67 meters from C. So now the total distance will be, so this value is now 10 only, 10 kN only. That is equivalent point load, half into 2 into 10. It acts at a distance of 2 plus 1 plus 0.67, that is 3.67. So it is also clockwise. And another thing is he has given one external moment here, which is anti-clockwise in the sense that we have to take as minus 20 because it is anti-clockwise. Suppose if it is given clockwise, we have to take plus 20 here. So that means when you are calculating Ma, at that time you have to consider this external moment, not during this calculation of Va. So if you simplify this, you are going to get 32.7 kilonewtons per kilonewton meter, which definitely acts in the anti-clockwise direction because it should be in the opposite direction of this moment due to the external given forces. So now these two are the reactions. Next, let us calculate the shear forces at different points on the beam. So what we do is, normally in the case of cantilever beam, always we take the distance from the free end. It is better to take the distance from the free end. That means, in other words, shear force at different sections is computed by seeing towards the free end. So if I want the shear force at D, FD, now I am going from the free end now. So FD will be 0 because if you see the right side of D, nothing is there. Therefore, shear force is 0. Suppose if you take shear force at C, if you want to calculate shear force at C, see to the right side of C because I am seeing towards the free end now. Free end is D. C to the right side of C. The sign convention for shear force is given here. This I have given in the last lecture also. So if you are seeing to the left side of the section, upward force is positive, downward force is negative. If you are seeing to the right side of the section, upward negative, downward positive. Now since we are seeing to the right side of the C, so it is downward force, therefore it is positive. So shear force will be your total triangular load, which is nothing but half into 10 into 2, which is 10 kilonewton. Now come to this point B now. You have 2 points here. I have told in the last class that at a point where the concentrated load is acting, you have 2 values of shear force, one just to the left and another just to the right side of the section. Now since I am moving from this end, first I will write FBR. FBR means shear force at the point just to the right of point B. So which is nothing but the same as FC, because no force exits from right side of B to C. So therefore whatever shear force is there at C, same shear force acts at BR also. So it is 10 kilonewton. Now coming to this FBL, left side of L. So if you are coming to, if you are here, if you see to the right side, in addition to this UDL, you can see this 8 kilonewton also. So it is downwards once again. You are seeing to the right side downward. Therefore you have to add them. So it is 10 plus 8, 18 kilonewton is the shear force just to the left of B. Then lastly we have to come to this shear force at A. Shear force at A is nothing but the reaction at A, which is 18 kilonewton. It is also positive. So that means if you plot the values of shear force by in a diagram, that means shear force diagram if you want to get. So write a horizontal line, mark all the values. Now I will mark from the right side, that is from the free end. Now at D it is 0, then at C it is 10, then FBR is 10, then FBL is 18. So there will be 2 values of shear force here. The difference is nothing but this whatever force is acting at that point B. So that is the difference. So here 10, then 18, then you have here also 18. So then we complete this diagram. When you are joining the points, so where this triangular load is acting, the shear force diagram profile is a parabola. So only from C to D is a parabola. Rest of the sections it is a straight line. So if you are using the simple method of drawing shear force diagram, so start from point A. You have an upward reaction 18 kilonewton, move upwards by 18. Then there is no force from A to B, so shear force remains constant. Then at B you have a downward force of 8 kilonewton. So come down by 8. So already you are at 18, minus 8 means 10 you are going to get. Then from B to C there is no force given, so therefore shear force remains constant. From C to D you have a linear UVL of total load equal to half into 2 into 10, which is nothing but 10. So you have to come down by 10. Because it is downwards, you have to come down by 10. So since the profile is a parabola, you have to draw a smooth parabola. So finally it ends up D. So you have to start from A, ending at D. So this is also in this way also method also you can draw the shear force diagram. Now coming to the bending moment. Bending moment is also calculated by seeing to the right side of the section, that is right side means by seeing to the free end. Okay, so now this is the sign convention for bending moment. So if X is the point of the section under consideration, whether it is left side or right side, upward forces give positive bending moment, downward forces give negative bending moment. So this upward forces give sagging type of bending moment, downward forces give hogging type of bending moment. So that I have explained in the earlier examples also. So if you once again take from the free end, first value of moment at D will be 0 because nothing is there to the right of D. So therefore value is 0, at the free end it is 0. Then MC here, bending moment at C to the right side you are seeing, and force is downwards. This force is downwards. Therefore it is a hogging, negative bending moment. So to calculate the negative Z bending moment, take this 10 kilonewton load, equivalent concentrated load, multiplied by the distance. Distance is 0.67. So minus 10 into 0.67. See here. So this is the minus 6.7 kilonewton meter is the bending moment at C. Next, coming to B. So at B you have an external moment given also. I have told you in the earlier problem that whenever at any point where an external moment is given, you have two values of bending moment. Once again, just to the right, just to the left. So to calculate just to the right, if you are here, see I have shown here at B he has given a moment of anti-clockwise moment of 20 km/meter. So, but here what happens? Since I am writing here and I am seeing to the right side of that, this 20 is not seen. 20 is not seen. That means only you have to take the moment due to this bending moment due to this triangle. So it will be minus 10 into 1 plus 0.67 distance. So that is the value. So minus 16.7 kilonewton-meter. Then coming to this point, left side of B. If you see to the right side of left of B, that means this point. If you are seeing right side, you will be having two things. One is this triangular road. Another one is this moment. This moment is seen now. When you are seeing from this point towards right, you can see this. So moment. So that means here moment due to this will be minus 10 into distance is 1 plus 0.67. Then this also we have to consider. This moment also we have to consider. See here how to take that. So this is given like this. You are seeing to the right side of this L, point L. You see the right side of L, you can see that it is like this. That means sagging. It is of sagging nature. Right side, it is sagging nature. Therefore, we have to add. It is positive. We have to add 20. Just we have to add that moment value. So if you simplify that, you will get 3.3. So already minus 16.7 will be there. Then you have to add that plus 20. So you will get positive value, 3.3 kilonewton-meter. So that means bending moment changes from minus 16.7 to 3.3 at the point B, which is an effect of this external moment. Now last point is A. Bending moment at A is nothing but the total algebraic sum of the moments of all these forces given to the right side of A, which is nothing but due to this it is 10 minus 10, all are minus because it is right side downward. Right side downward, so negative. So from A, this distance is 2 plus 1 plus 0.67, 3.67. So minus 10 into 3.67 is the bending moment due to this. Then minus 8 into 2 is the bending moment due to this. And this is plus 20. Just we have to add plus 20. You can see here. So the value becomes minus 32.7 kilonewton-meter. So that is the actual maximum value. At the fixed end, you have the maximum value of bending moment which is hogging in nature. So if you plot all those values starting from this pre-end at D, MD is 0, then you move in the same order. So MC is minus 6.7, minus means you have to plot below the line which is hogging. Then MBR minus 16.7, here minus 16.7, then MBL 3.3, it is positive, therefore you have to plot above the line. Then MA is minus 32.7, once again below the line, and it closes. So here, how to join the points, that is very important. So only in the portion CD where the triangular node is acting, profile of a bending moment diagram is a cubic parabola. So this is a cubic parabola. Just draw a smooth curve and write it there. So from C to D, it is cubic parabola. If it is UDL, it is parabola. Since it is UVL, it is cubic parabola from C to D. Rest of them are straight lines. But when you are joining, you should be very careful. So in whatever order you have taken the values, in the same order you try to join the points. D to C, it is cubic parabola. C to B, it is straight line. Then B, you have two values. So the difference between these two values is nothing but 20. You can see that this is minus 16.7, this is plus 3.3. Total difference is 20. So 20, that is nothing but your external moment given in the problem. Then from B to A, it is straight line. So this is how you have to draw the bending moment diagram. Now I have just given here the profiles. So already I have explained this. So if it is a concentrated load, bending moment diagram is a straight line, shear force diagram is also a straight line. If it is a UDL, uniformly distributed load, bending moment diagram is a parabola, shear force diagram is a linearly decreasing line. So like this. linearly decreasing line. So because UDL acts downwards like this, so it is a linearly decreasing line. Then if it is a triangular load, bending moment diagram is a cubic parabola because it contains x cube term, and shear force diagram is a parabola because it contains a x square term. So cantilever beam problems are very easy. So only one problem I have explained here. So depending on the type of the load, so your profile of BMD and SFD will vary. So this is the general method. Even without finding the reactions also, you can draw the BMD and SFD. When you are seeing to the right side of this right side of that is towards the free end, you need not find the reactions. So this you need not find. Only directly you can start from here because nowhere I have used the reaction value. So, but in the case of simply supported beam, you have to must and should find the reactions. Then only you have to proceed to find the BMD and SFD. Thank you.